then the available computational resources and all, it will be very much important for us to decide. So we can't go for very complex models that take a lot of time to train. Likewise, also we have to check the desired level of interpretability as well. Now, if it is a neural network or something that we are using, it works as a black box, so it's a bit hard to interpret. But if we are selecting a simple machine learning algorithm, so maybe it has a higher level of interpretability. So it's a trade-off between all these things. So this is a small graph that kind of shows how the interpretability and the accuracy has a trade-off. So if you have the highly accurate, if you want highly accurate models, if you want have non-linear relationships, non-smooth relationships, there are several algorithms that you can use. Also, if you want highly interpretable models, and if they are linear and smooth and also easy to compute, there are a set of other machine learning algorithms you can use. So you have to kind of make the decision to see what is the algorithm you should be using. Okay, yeah. So what else we have to look at when we are choosing an algorithm? First thing, like I mentioned, we have to understand the problem. So we have to determine whether our problem is a classification, regression, clustering, or any other type of task. So this helps us to narrow down the choices of algorithms we have. So if anyone from the audience, if you have already kind of guessed, for classification problem that we have already in hand, can someone tell me an example algorithm that I can use to get some predictions done? Anyone? Because it's me who has been talking for a while now, so I would like to hear someone else's voice. Anyone who can kind of tell me, okay, you can go ahead with this algorithm. I mean, even if the answer is wrong, it's all right. Can I just pick someone randomly? Okay. Uh, so there's someone called Natali. So if you are comfortable, can you kind of unmute and give me a example? If you don't know, just say you don't know. That's also fine. It seems like she's very silent. I'll check with one more other person, and if not, I'll kind of go ahead with the interest of time. Yeah, so Minusha, would you like to kind of share some thoughts? Yeah, no worries. Okay. Yeah, I'll go ahead with the this one. Okay, so for the classification problems, like I mentioned, we can use logistic regression, decision trees, random forest, and many other algorithms as well. Okay, so the other problem, the other thing that we can consider is the size of data set we have. So if you have a large data set with many features, you may prefer scalable algorithms like stochastic gradient descent, random forest, gradient boosting machines. Likewise, for smaller data sets, you can consider algorithms that might be more computationally expensive but offer high accuracy. Right. So also we can check for linearity. So if our problem exhibits really linear relationships between features and the target variable, linear models like linear regression, logistic regression, or support vector machines might be suitable. So if it is a regression case, okay, like if it is a classification problem, so both are possible. So for nonlinear relationships, you may need more complex models like decision trees, random forest, or neural network. Also, we can evaluate the model complexity, considering the trade-off between model complexity and the interpretability. So simple models like linear regression are very easy to interpret, but may not capture complex relationships on data. So they can't really look into all these complex relationships that is hidden inside data. So it will only do a very simple job actually. But on the other hand, complex problems like models, like deep learning models, like neural networks, they can capture intricate patterns, but it is very hard for us to interpret because they work like a black box. And the other thing is handling imbalanced data. So if our data set is imbalanced, that means if we are telling that our data set is imbalanced, that means one class is significantly more frequent than the other one. So we have to consider algorithms that can handle class imbalance well, such as random forest, gradient boosting, or techniques like oversampling and undersampling. Other than that, if we are dealing with high dimensional data, so mostly these high dimensional data, they occur in fields like bioinformatics and also protein data sets. And also for high dimensional data that has many features, algorithms like random forest, gradient boosting, support vector machines, with a kernel trick might work well. So dimensionality reduction techniques like PCA, or principal component analysis we call it, also, or feature selection can also be considered so that we can simplify our data set. Also, we can look into ensemble methods. So ensemble methods are like random forest, gradient boosting, and NADA boost often provide a robust performance by combining multiple base learners. So they are generally a good choice when individual models fail to perform well. Yeah. So other than that, we have to consider algorithms assumptions as well. So certain algorithms will have certain assumptions. Now, for example, linear models, they assume linear relationship between feature and the target variable. But if it is not the case, it is going to be a mess, right? So we have to make sure the algorithms that we are using, if it has some assumptions, our data are aligning with those assumptions. So while decision tree based models like hierarchical decisions based on features, so we can kind of use those instead. And also we have to think about how to do the experimenting and the validation part. Experimenting with multiple algorithms and evaluating their performance using cross-validation or holdout validation is helpful. So holdout validation is what I just showed you like a few slides back, having some data withheld so that we can do some validations. Cross validations, I'll just explain you in a bit about what it is and why it is needed. So we can choose algorithms that perform best based on evaluation metrics relevant to our problem. Okay, so this is the answer for the problem that I asked, right? So algorithms that can be used for a classification problem. So why I'm kind of discussing more on the classification problem is because of the data set that we are using. It's a classification problem that we are dealing with. So that is why I'm kind of more focused into classification algorithms and like talking about classification more. So for a classification problem, we can go ahead with logistic regression, decision trees, random forest, also gradient boosting machines, support vector machines, k-nearest neighbors, and so on. So these are just few examples. You can have many other algorithms as well to do this task. Right. Let's move on to model training and testing part. So you know that we have done the splitting part, and you know what are the things to consider when we are choosing a model, and also what models you can use when you're dealing with the classification problem. So the next step is to see how the training and testing should be done. Yeah. So it's fairly simple that we have done all the work before. Already we have kind of done all the necessary steps. So we can train the model using training data set. So we ensure that our training data set is properly formatted and pre-processed. So all these feature selections, all these pre-processing for missing data, handling outliers, all the also like for categorical variables, since our machine learning models can't process categorical variables, we have done encoding. So all these things has already been done. So this may involve, like I mentioned, the handling missing values and everything. So any other necessary data transformation as well. So if we want to standardize, if we want to normalize, those things also can be done. And then we can instantiate the model. So instantiate the model that can be done using the machine learning library that we prefer. So the recommended one is the scikit-learn in Python for this particular case, right? So to fit the model to training data, you can use .fit method of the model object to train the model on the training data set. So we can pass the features and the target variable of the training data set as argument to the fit method. So this is just a example code snippet to use logistic regression as a model, right? So this from the scalar linear model, we are importing the logistic regression algorithm, and then we instantiate the model as model equals logistic regression, and then we can train the model using the x and y's of the training data set we have. So x trains means all our predictor variables in the training data set. Y trains means the output or the actual values of the stock variable that we have in our training data set. Then we can move on to testing once the training process is completed. So usually the training phase, it can take some time depending on how complex our model is. So it can take up to days, or it can take up to hours to train that model, basically, depending on how complex it is and how much of data we have and dealing with. So to ensure that we are now checking our predictions with the trained model, we can use our test data set. So test data set also, it is also should be properly formatted and pre-processed. So whatever the feature things that, whatever the transformations, whatever the remedies that we did for the training data set, it should be done for our testing data set as well. And also it should have same features as the training data set, but with unseen target variables. So we are not going to feed our labels into the algorithm, right? So we are going to use the train model for predictions. So we use our model to pass the X test, which means our test variables only the predictor variables only, not our response variable, and we are going to pass it to our trained model, and we are going to get some predictions. Why predict? These are predictions that we are going to get. And then we can do some evaluations with those numbers by comparing our predicted values versus the Y test values that we have, the actual values for that instances we have. Okay, now let's move into the model evaluation metrics. Let's see how we can evaluate our predictions that we already took in this step, right? Okay. Evaluation metrics are quantitative measures. Those are used to assess performance and effectiveness of statistical or machine learning model. So these metrics provide insights into how well the model is performing and help in comparing different models and algorithms. So for a regression case, we can use this MSPE, MSAE, the mean squared error, mean squared average error, R squared, adjusted R squared, likewise. And for classification problems, we can use precision, recall, ROC curve, AUC curve, accuracy, log loss, and all. Also, for unsupervised models, also there are some evaluation metrics that we can use. And also there are for other cases also, like for NLP, the natural language processing, and all. Also there are some other scores that we can use. So our focus today will be on this classification model evaluation. So to evaluate a classification model, we can use something called a confusion matrix. So let's see how we can evaluate a classification model using confusion matrix. First, we have to understand what is a confusion matrix, right? Okay, now for example, just think about a scenario like this. Okay, so my goal is to, uh, so my data set has some triangles, some squares, some circles. So my goal is to create the classification algorithm that will help me to divide this into correct groups. So so if my classification algorithm is working very well, that means it will correctly classify my triangles. It will correctly classify my circles as circles. It will correctly classify my squares as squares, right? But this is not going to happen in the real world scenario. So our models are not that perfect. So if it is perfect like this, that means there is a problem. Okay, so 100% accuracy, it's not actually a good thing. Somewhere we have messed up. So we have to find out where the problem is. Sometimes we might have fed in the target variable itself as a feature. So we have to be cautious. So if the model is not performing well, or in the real world scenario, it is not going to be able to classify all the observations correctly into the respective categories as demonstrated below. So my classification algorithm here, it has classified mostly triangles, but also some circles, one circle and a triangle also as a, sorry, a square as a triangle here, right? Also, here it has correctly classified two circles, but it has classified a triangle and a square as a circle too, right? So similarly here also, three squares, they have correctly classified as squares, but it has incorrectly classified a square, a circle as well as a triangle, right? So that means there is a, so this was our expectation and this is our reality, right? So there is a difference between these two. Confusion metrics help us to understand such scenarios. So it kind of used to demonstrate the performance of a classification model. So it compares the predicted class labels with the actual class labels and provide information about true positive, true negative, false positive, and false negatives. So this confusion matrix values that we are talking about, this true positive, true negative, positive, false negative, this actually could be confusing too, ironically. So I'll try to kind of explain you what it actually means. And then if you have any questions on this one, just ask if it is not processing in your head very well, okay? For my classification task, okay, my two classes that I'm, or two categories that I'm hoping to classify are going to be this positive and negatives, okay? So you can actually think of this positive and negative as positive for stroke and negative for stroke. So one, if the person has a stroke, so if that person is actually having a stroke, you can think of it as a positive. And if that person is not having a stroke, you can think of it as negative. So these are the two categories that I'm interested in. So all the observations will fall either into positive or negative. So we can only have two outcomes, which are either having a stroke or not having a stroke, right? So then we can look at two things. One is my actual values, which is the actual category to which the observation is belongs to. And also I can have predicted values, which is the categories to which the model has allocated the observations into. Okay, something like this. Okay, let me try if I can. Yeah. So one person, if this is the case, right? If one person is having a stroke, my algorithm, it can actually say that this person has a stroke, right? Otherwise, if this person is having a stroke, sometimes it will misclassify it as not having a stroke. So this is my actuals, and this is my my predicted values, right? So my predicted values. Okay, so these numbers we can take to all the data points we have. So sometimes if it is 0, 0 we have, but this is correctly classified, this is incorrectly classified, likewise. Okay. Now, using these numbers, I can categorize these instances into any of these scenarios. So in this particular matrix that I have drawn here, I have my predicted values and my actual values. So my actual values can be positive and negative, right? So this person has a stroke, this person actually has a stroke, and this person has no stroke. Okay, so the actual scenario is this. Okay. Similarly, the predicted values can also have classify someone as stroke and classify someone as no stroke. Okay, no stroke. So if both the cases are positive and matching, that means if it is positive in both the cases, for predicted value is also positive and the actual value is also positive, so then we call this as my true positives. So in here I have one true positive case. This is a true positive case. Okay, and then I can have true negatives also, right? So that means the person has no stroke and my predicted value also says no stroke. So this is a example for a true negative. Okay, then we can have false positive also. So that means the actual person, he has no stroke, but my prediction says that he has a stroke. So it is a false positive, right? So this scenario. So my actual value is 0. But in my predictions, it says it is positive. So this is a false positive. And then we have false negatives also, right? So false positive done, false negative done, sorry, true negatives done, true positives done, and we are left with false negatives. For false negatives are the scenarios where the actual value is actually positive, but my predicted value says the otherwise, right? So he has a stroke, but my predicted value says no stroke. So it says no stroke. So such scenarios, this scenario, right? So this is a false negative. Okay, so this is how we are going to have different numbers for each of these values, right? So in this my case, since I just showed you 4 data points, every one of these squares will have 1, 1, 1 and 1. Okay, so but in reality we will have other numbers here. Then let's see what are the matrices that we can calculate out of this confusion matrix. Okay, to measure the accuracy of my machine learning algorithm, the classification algorithm, uh, we use several set of measures. Okay, so we can start with accuracy. So accuracy is a common evaluation matrix that measures the proportion of correctly classified instances out of the total instances in the test data. So if we just calculate a number here, so the accuracy for the instance that I was talking about will be, I had just one true positive and one true negative, right? So 2 divided by 4, because I had 4 data points, true positive plus false positive plus false negative plus true negative. So everything adds up to 4. And here on top, I will have true positives and true negatives. So the accuracy, you can think of it as a proportion of correctly classified instances out of the total instances. So correctly classified instances, this can be positive or negative. It doesn't matter, right? Then we have precision. So the precision is the ratio of true positives to the sum of true positives and false positives. So it measures the accuracy of positive predictions made by the classifier. So in accuracy, it's a common measure, right? Whether it's negative or positive, it doesn't matter. But in precision, we are specifically interested in positive instances. So number of true positives I had, again 1. True positives plus false positives, I had 2. Okay. So here the precision is more used for think about true the positive scenarios, basically to positive predictions that it had made. Then we have another 2. Okay, so accuracy, precision, and then we have recall or sensitivity. So the ratio to true positives to the summation of true positive and false negatives are called the recall. Okay, so it measures the classifier's ability to correctly identify positive instances. Earlier, here we are checking the ability to correctly identify positive instances. So out of the positive instances we have, out of all the positive instances we have, so out of all the positive instances means the true positives and the false negatives, right? So this is also actually positive, this is also actually positive. So out of all the positive instances, what is the number of positive instances it could classify correctly, right? So if just don't confuse between this and the earlier precision, right? In precision, we were more interested to see how many times it correctly classifies all these as the positive numbers, right? But here I just go back and show you the precision was more on the positive predictions made by the classifier, right? So we are checking false positives, that means positive predictions in both the case, true positives as well as false positives. But in this case, in my recall case or the sensitivity case, I'm looking at the correctly identified positive instances. Okay, so that's the difference between the precision and the sensitivity. So here also this, and then finally we have something called F1 score. So this is the harmonic mean of the precision and recall. So it provides a balance between precision and recall, especially in imbalanced data set. So our data set is actually imbalanced data set. So if we want to choose a matrix to measure the accuracy, we better go with the F1 score. Okay, right. That's about the confusion matrix and the values we can get out of it. So we discussed accuracy to check how correctly classifying all the instances out of total instances we have. And then we discussed about precision, where we check the positive predictions made by the classifier. And we discussed about the recall, where we check the correctly identified positive instances. And then we have the F1 score, which provides a balance between the precision and the recall. Okay. Then let's move into discussing about cross-validation. So before moving into cross-validation is actually a resampling technique. So resampling techniques are methods used in statistics and machine learning to create new data sets or obtain new samples from existing data. So these techniques are particularly useful for various purposes, such as assessing model performance, dealing with imbalanced data sets, and estimating uncertainty. So one such resampling technique is actually cross-validation. Now, let's just take this particular example. Okay, so I have a data set. I want to predict the rent per year using all these predictor variables I have. Distance to the next pet shop, size, year built, and the distance from the center, right? So my intention is that I'm training using this data set, and then I use some new data from my test data set to see how the predictions work, right? So cross-validation, it allows us to compare different machine learning methods and get a sense of how well they work. So now I told you in the beginning that when I'm dividing my data set, I can divide it into two, right? It's either 80 to 20, 70 to 30, 90 to 10 or whatever, right? So imagine now here I want to divide this into two. First, like 75% for training and 25% for testing, right? Then we can actually do this splitting in different places, right? It doesn't have to be the first 75% for training and the last 25% for testing, right? I can either choose last 75% for training and then first 25% for testing purposes. And also I can choose 75% from the middle also, right? So there are different ways of there were different ways we can change, or we can divide our data set into two. Then in all these instances, we are going to get different results, right? So depending on the data set that we are choosing for training data, we are going to get different outputs, right? So it's not going to be the same in these three instances. So cross-validation, it helps us to use all these different selections one at a time and summarize results at the end. So with cross-validations, we don't really have to worry about this thing anymore, like whether to choose first 75%, last 75% or so on. This helps us to use different ways of splitting. Now, just imagine this as my data set, okay? So this is my data set, and I can divide this into 4 blocks, okay? So I'm going to divide this one into 4 blocks. So I'm going to use 2 rows. So one block as my training data and the rest as my testing data. Okay, so each of these instances that you see, the blue ones I have kept as my training data, and the gray colored one or purple colored ones are taken as my testing data set. Okay, so why cross-validation is very helpful is because data is very limited, right? So training and testing on the same portion of data does not give us an accurate view of how our model performs. With cross-validation, we can take the maximum out of the data we have. So in cross-validation, we are going to use train and evaluate our model on a portion of our data before repartitioning and evaluate it on the new portion. So we will use this one and we would do some evaluation, and then we choose another portion, and then we are going to choose this one as our training set and do another validation likewise, right? So it's an iterative process. In each of the iteration, like I have shown here, so if I'm having these data sets, I might choose these 2 data points as my training set, and the rest as my, the orange colored ones as my training set, and these 2 colored ones as my testing set for the first instance. And I can take a measure, say F1 score I'm measuring, so I will get a F1 score here, right? And in the second instances, now I have a different set of training data and a different set of testing data, right? So here also I will get a F1 score, and it will be another number, not this measure one, right? So similarly, in the other two instances also, I might have two other measures, right? So, and then we can average it out and get a value for the entire exercise. Okay. So in this case, since the data is divided into 4 blocks, we called it a 4-fold cross-validation, but we can have any other number also here, right? So we call this exercise K-fold cross-validation. So one common approach to cross-validation is K-fold cross-validation. There are some other methods also that we can use for cross-validation, but the most simplest and the most used one is this K-fold cross-validation. So in this method, the training set is further divided into K small subsets or folds. The machine learning model is trained K times each time using K minus 1 fold for training and different fold for validation or testing. So each fold takes turns being the validation set, while the remaining K minus 1 folds are used for training. After the K training iterations, you will have K different models, and each model's performance is evaluated on the corresponding validation fold. Overall performance of the model is then computed by averaging the evaluation metrics. So accuracy or precision or recall or F1 score that we obtained from each iteration. So just to kind of recap, so this was our data set, right? And we divided it into 4 blocks, and iteratively we use each one of these blocks as my test data set, and I started training with the other 3, right? So K minus 1 is 3 here. K is 4 here. And then I iterated it 4 times. And 4 times I trained the model and I tested with this the model with my testing data set, and then I obtain 4 different matrices, say F1 score, and then I can average it out and get a value. Okay. So advantages of cross-validation. Cross-validation helps us to provide a more reliable estimate of a model performance than just using a single train test split. So it reduces the risk of getting an overly optimistic or pessimistic performance estimate. And also, it maximizes the use of available data. Even though we have a very limited number of data, now we are kind of iterating this data set into different, by like repartitioning into different testing and training data sets, right? Even though the data is limited, we have gotten the maximum use out of it. The value of K depends on the size of your data set and the balance between training time and evaluation accuracy. So common choices for K are 5 or 10, but you can experiment with different values. Okay. Yeah. Then the last topic for the day is hyperparameter tuning. So now we have split our data, we have trained our data, and then we know how to do the evaluation, also how to get the maximum benefits out of the data we have using our cross-validation. And then it is time for us to do some hyperparameter tuning. Okay. In machine learning, there are 2 types of parameters. So hyperparameters and model parameters. So they serve different roles in the training and optimization process of the machine learning model. Okay. Model parameters are internal to the model and are learned during the training process. So what happens is when we try to, I mentioned in the beginning that at the end of the day, certain machine learning algorithms that we use will create some sort of a mathematical function with some parameters. Okay, so model parameters are internal to the model and are learned during the training process. They are variables or coefficients that models learns from the training data to make predictions. So they look at our training data and they try to understand the algorithm is trying to understand, okay, what are the patterns I can see in my training data, and with those patterns it kind of learns some parameters, So model parameters, they represent that knowledge or pattern extracted from the data during training. So weights and biases in neural network, coefficients in linear regression, and also split points in decision trees are some examples for our model parameters. So model parameters are adjusted during training through optimization algorithms such as gradient descent, where the goal is to minimize the loss function by updating the model parameters iteratively. So if you don't understand what is gradient descent, just think of it as we are checking the minimal difference between the predictions and the actual values we have. It's just a sort of an algorithm to achieve that faster. Okay, right. Then let's see what is a hyperparameter. A hyperparameter is a configuration that is external to the model. So that means it is not actually learned during the process of training, and its values cannot be estimated from data. So the data will not help us to choose the hyperparameter values. So these parameters are typically set prior to the training process and remain constant during the training. So this is usually these hyperparameters we have to set it by ourselves prior to training process, and then it will remain constant during the training. Hyperparameters are not directly learned from data. Instead, they control aspects of the learning process and the overall behavior of the machine learning algorithm. For example, learning rate, number of hidden layers in a neural network, regularization strength, and the kernel type in support vector machines. So those are some of the hyperparameters we can use. Okay. Let's see how to identify the hyperparameters of the chosen. So how to do the hyperparameter tuning actually, okay? So first we have to identify the hyperparameters of the chosen machine learning algorithm that we are going to optimize. So depending on the algorithm we have, there will be different parameters that we can work with. Now, for example, this could be a learning rate, number of estimators for ensemble method, maximum depth for a decision tree, also regularization strength, etc. So, hyperparameter tuning, uh, it can be done using these search strategies. Okay, so we have something called grid search, something called random search, as well as Bayesian optimization. So grid search and the random search is the most popular ones. And grid search exhaustively search through a specified set of hyperparameters, and random search randomly sample hyperparameters from a specified distribution. In Bayesian optimization, it uses a probabilistic method to select the next set of hyperparameters based on previous evaluations. I'll just explain a little more on the grid search and the random search. Okay. Grid search, it looks through each combination of hyperparameters. This means that every combination of specified hyperparameters values will be tried. So it's not going to be a random thing. Okay. So it's going to check all the every combination of the specified hyperparameter values. Okay. But random search, it uses random combination of hyperparameters. This means that is not going to check all of the parameter values or combinations. Instead, parameters will be sampled with fixed number of iterations given by n iter. Okay. So random search would be advised to use over grid search when the searching space is high, meaning that there are more than 3 dimensions as more than 3 dimensions. That means we are looking at multiple hyperparameters, not just one, not just two, more than 3. Okay. So if it is the case, random search is able to explore a wider hyperparameter space. Because if we are going to use grid search, it is going to be very slow because it's going to check for all the combinations, which is going to be a very high number, right? So when there are many parameters, random search could be preferred, as too many parameters will increase time complexity of grid search, because grid search has to check for each and every combination. It is going to take a lot of time to compute all these values. However, through grid search can be very even though it is very computationally expensive, it is an exhaustive search. It is useful for looking through all the combinations of specified hyperparameters. So it will give us better results, but only thing is the time complexity it takes, because that it has to check all the possible combinations. So let's just go through an example and see how hyperparameter optimization can be done, okay, using a grid search and random search. So this particular example that code snippet that I'm going to show you, it is for gradient boosting regressor. So it is only for example purpose here. It is not going to be suitable for our data set, because it is gradient boosting regressor that I am using, not a classifier. Okay. So I'm going to look at 5 hyperparameters. One is number of estimators. So in gradient boosting also, I'm looking at a random forest, right? So in the random forest, I can have multiple decision trees. So the number of estimators is the number of trees in the forest. Okay, the higher number of trees can be better for learning the data, but higher number can increase the time it takes for the training processes. So the more decision trees I have, the better my learning will be, but unfortunately it will take some more time for training process, right? So I have to find a sweet spot for my number of estimators. Similarly, learning rate. So this is the rate at which it controls the weighting of added new trees. And then I have maximum depth. So this is the maximum tree depth. So for a given decision tree, how many levels I'm going to go further into. So the depth of the tree relates to how much information of the data is captured. So a deeper depth captures more information. Even though the deeper depth captures more information, again, it will increase the computational complexity. And also I have my minimum sample leaf. This is the minimum required number of samples to be at a leaf node, and also the minimum sample split. This is the minimum required number of samples to split an internal node. So for a given leaf node, what is the number of samples I should have? It is whether it is going to be one or more or likewise. Okay, right. So this is how we can use random search from the model selection to get some best parameters. Okay, so in this particular code, I have specified some values for number of estimators, learn rates, maximum depth, minimum sample leaf, minimum sample split. So I have given 2 numbers for each scenario. For number of estimators, I'm going to either set it to 500 to 1000. Here also learning rate 0.02 or 0.05. Maximum depth also 1 or 2. Minimum sample leaf and minimum sample split 5 or 10. Okay. So this is my parameter grid. My parameter grid, in my parameter grid, I will specify, okay, what is the number of estimators, and I will say this number of estimators I have specified here in the above. Okay. And similarly for the other ones also, I have given the values. And then I'm going to initialize my random search using this randomized search CV. And I'm telling that for the gradient boosting regressor, with the loss function of Huber, give me so I'm just passing my parameter grid as well as my random state, the number of iterations it should do, the cross validation, verbose, and the number of jumps. Okay, and I'm going to feed my random search and for my training data set. And then it will output me the random search best parameters like this. So random search suggests me to take 0.05 for learning rate, maximum depth 2, minimum sample like 5, minimum sample split 10, number of estimated 1000. Okay. So similarly, grid search also can be done using the same thing. Here also you will have this some similar result. Okay, but only thing here, the change is that I'm now using the grid search CV. Earlier I was using randomized search CV. Okay. So with hyperparameter tuning, I can choose an appropriate performance metric to evaluate the model during the hyperparameter tuning. The choice of metric depending on the problem. So it could be accuracy, precision, recall, F1 score for classification, or mean squared error, or R squared for regression. Okay. And then I can split the training data into multiple folds as well for cross-validation. So this helps to ensure that the hyperparameters generalize well across different subsets of the data. And then it can also iterate over different combinations of hyperparameters using the chosen search strategy, just like we did here. Okay. And we can train a model with each set of hyperparameters on the training data and evaluate the model performance on the validation set using the chosen scoring metric and get some values. Okay. So after evaluating all models, select the set of parameters that result in the best performance on the validation set. Once you have selected the best hyperparameters, evaluate the final model on the test data to assess its performance on unseen data. Right? So we use the training data set to do all this hyperparameter optimization, or else you can use that validation data set also that I mentioned earlier. And then we can come up with the best set of hyperparameters. And then we can finally use those and evaluate the final model on the test data set to assess its performance on unseen data. So if the performance on the test data is not satisfactory, you may need to revisit earlier steps. So it's an iterative process. Such as, so we will have to look back and see what has gone wrong, like pre-processing the data, feature engineering, selecting different machine learning algorithms likewise. Okay. All right. So that's all for the theoretical part. Before we move on to the demonstration, do you have any questions? Any questions? Okay, I think I'll just answer these questions that I see in the chat. Okay, I think that's fun. Okay. My question is regarding the splitting data. As per your explanation, you have split data as test, train, and validation. Don't we need to combine all these three data sets for taking final model for the for all data? No, we don't have to. Okay, so the final model that we are going. So our intention of developing a machine learning model is actually to use it for future data. Okay, so in the training process, what we are doing is, in the training and testing process, okay, what we are doing is we work on what the data we already have. Now, for example, I'll just kind of discuss this with a real world scenario, okay? So I want to predict my fresh items, fresh vegetable prices for my supermarket for the upcoming week. Okay, so I don't have values for upcoming week, right? So now only thing that I know is the historic data I have. So the model building part I will be using, I will be doing using that historic data I have. So instead of using all this historic data I have in my hand, I'm going to keep aside few, like my testing and the validation set aside to do the training of my model. Okay, so I'm going to use a set of data I already have in my hand to do some training and build some sort of algorithm. And then to see if my model is working properly, I'm going to use that model that I have developed using the training data applied into my testing data. So the testing data, once I feed it into testing data, I already have, because it is again, it is historic data that I'm using, right? So I already know the actual values, but I know the actual values. So I'm going to use my actual values compared with the predictions that I have made and check for the accuracy. So then I realize, okay, with the calculation I did, I have 80% of accuracy. So with this one, my expectation is this mathematical function or the model or the algorithm that I develop will work on the same accuracy for my future data as well. Like that means even for the actual unseen data, right? Because when I'm working for the when I'm predicting for the next week, I don't have those values at all, right? So I have to kind of uh, make the assumption that my model will work as it was working for the testing data set for my actual real world future predictions as well. So, I mean, we don't really have to do any kind of a combination or anything to take a final model for all the data. We don't do such thing. Uh, any other questions? Okay. Normally, what are the models we can use for regression problems with small data set except for linear regression? So you can use decision tree regressor, even random forest regressor, those ones. I mean, you can search it up. There are many other algorithms also. So, I mean, usually you can go for random forest regressor or decision tree regressors depending on your situation. But if it is a very small data set, it's usually, I mean, machine learning algorithm models in general, it works well for big data sets. Like, I mean, if you have a considerable amount of data. So if it is a really small data set, it's good to stick to a very traditional model, like linear regression or multiple linear regression or like polynomial or whatever. Okay. Yeah. So I think there's no more questions. I'll move into the demonstration as well. Okay. Can someone confirm if you can see the Google Colab notebook now?
Still not.
Is it with? Sorry?
Still not.
Still not. Give me a second. I'll do a new share. So I think last time I was. Okay. Is it visible now?
Yes.
Okay. Okay. Right. Yeah, so for this one, I think you're already familiar with this mounting part, right? So we can mount our drive for Google Colab and add our data into it, and then we can read from there, right? For the data reading part, I'm using pandas. So the first set of computations I have actually taken from your last week workshop, right? Because she did all the feature engineering that is needed, right? So I'm not going to explain much on that content. So I'm using this data set. This is my data set, right? So I have ID, gender, age, hypertension, heart disease, these things, right? And you might notice that in BMI, I have some non-values. Also the smoking status, resident type, work type, all these are categorical values, okay? So I need to do some sort of transformations and like do some encoding, as well as I have to do some remedies for null values as well, right? So what I decided to do was that I decided to drop the null values I have. But if the values number is very high, we can actually drop those numbers. But if it is something that we can impute, we can actually impute also, right? It doesn't, I mean, it's not mandatory for us to drop null values every time. Okay, then I'm going to encode my categorical data columns. Here I'm taking my I'm dropping age, BMI, and average glucose levels, which are actually the numerical variables I see here. And then I'm going to check the categorical data that I'm having. So ID, gender, hypertension, all these things are going as a this one, right? What do you call a categorical data frame, right? So then I'm going to do one hot encoding for these columns, gender, hypertension, heart disease, ever married, work type, resident type, and smoking state. So that will transform my data set into something like this, right? So now instead of having just the gender column, I will have gender female and gender male, and also gender other. Similarly, for hypertension also, I will have hypertension 0 and hypertension 1. Similarly, for other instances also, it will give me all the possible outputs, or like all the possible classes these categorical variables can have, and it will create a column for those. Okay, so I hope you are kind of clear on this one. And I can do the same here also using the get dummies as well. Okay, then I'm going to use this transform data set for my future predictions. Okay, but I had to do some treatment for imbalanced data because my data set had more more no strokes than people with strokes. So basically, it was imbalanced, right? Um, the stroke status had a imbalance in the stroke status had an imbalance in its data, right? So what I did was or what like in last week's class, what you did was that you did some oversampling, right? So with oversampling, we have created some synthetic samples for minority class, right? Now, instead of having 156 positive cases, now we have 3,771 classes, instances for stocks also. So I'm going to go ahead with this data set for future development. Okay. All right. So now the uh, models that I can use, right? So I have chosen for this case, I have chosen three types of models. One is a decision tree, and the other one is logistic regression, and the other one is like GAB. Okay, then GBM. Now I'm going to use all these three models. There could be other models also that I can use. Okay, so this is just randomly I decided to go ahead with these three. Okay, and I'm going to check for my accuracies and all. Okay, so in order to do that, I created this definition for a model. Okay, so it's just some few steps combined together, putting like and compiled it into a function that I can easily call. Okay, so this is a function that I have created with some what do you call standard code snippets. So that is what we are doing when we actually building pipelines, model pipelines in real world also. Okay, so we are not going to have a notebook or anything like this in this big. Okay, so we have to properly structure it in a with following all the best practices for coding. Okay, so usually if we are having, I mean, if we are doing some sort of a what do you call uh, now for example here I'm trying to build a model, right? So if I'm doing some steps together to achieve something at the end, I would kind of compile them together into a function, and I will be calling that function. So this definition I have given for model. Okay, so it first it would fit a model. So if I'm specifying a model, it will first fit the model to my training data set. So my training, the data is already split into two, right? So that in the training data, I have my x's and y's. So for this x and y, I will fit my model, and then I will get a score for my model as well. And then I will check the training score as well as my testing score, and I check the prediction, and I'm going to take the predictions on my test data as well. Okay? And then I'm going to create the confusion matrix that I showed you, and I'm going to display that as well. Okay, so now this particular code snippet, it is to instantiate the decision tree classifier. Okay, so what I do is this, for this model function that I created, I'm going to pass my D classifier or my decision tree classifier. Okay, so this is the outcome of that. So it prints the testing score. That means from the testing, for the testing data set, I'm getting a 88% accuracy, which is good. And also it shows me how the labels are divided into different the truth and the actual labels and the predicted labels, how the confusion matrix is formed. Okay, so I can do this one for any other model also, but here it is for the decision tree that I have done. Okay, so if you remember the confusion matrix, now the confusion matrix I'm looking at is actually for the test data set. Okay, so I'm checking my y values for the test or the actual values of test against my predictions for the test value. Okay, and I see that I have correctly classified 863 negative instances, and I have correctly classified 66 positive instances, right? Positive star with positive, sorry, only 8 positive ones with positive. And then I have incorrectly classified not stroke people with no strokes as strokes 66 times, and then I have incorrectly classified people with strokes as no strokes 45 times. Okay, so this is my, sorry, this is my confusion matrix. Okay, this is how you would fit a decision tree classifier into your data. And then I'll just show you how the cross validation also can be done. Okay. Again, I'm going to use logistic regression, k-nearest neighbors classifier, the support vector machine classifier, as well as decision trees, random forest and XGB classifiers. But I think I have added only 1, 2, 3, 4, 5. No, I think I have added everything here also. For my cross validation. Okay, here even though I'm importing all these time series split, k-fold, stratified k-fold, group k-fold and all, I'm using only the k-fold method. Okay, and for metrics I have imported the accuracy scores, the confusion matrix and all. Okay, yeah, and I just show you what happens here, right? So in models, I'm going to append my models as a logistic regression, SVM, k-nearest neighbor, decision tree, random forest, and XGBoost. So what I'm going to do is I'm going to now I'm not going to just stick to one model, but I'm going to uh, train multiple models and see how the things work, right? So here for m in range length models, that means from here the number of models that I have specified, I'm going to choose one model and then I'm going to fit that model similarly to my training data set, and then I'm going to take the predictions, I'm going to take the confusion matrix also, and I'm going to calculate the accuracies. You also, I have, when I'm calculating the accuracies, I have here specified the number of k-folds or the validations that I'm going to do, right? The rock curve, it's not really necessary, even though I have added here the precision score and recall, and the F1 score is important. So you can then look at the accuracy score. So I'm just printing out the accuracy score, the k-fold validation mean accuracy. So that means what happens is, now I'm taking logistic regression. Okay, I'm taking all this, I'm doing all this, and here I'm the logistic regression itself is trained 10 times using k-fold validation. Okay, so SVM also I'm taking, and then I'm doing a tenfold validation. Okay, so similarly for others as well. So that is why this CV is 10. Okay, and then for each model that I'm using, I'm printing all these accuracy scores, k-fold validation, standard deviation, and precision recall, those things. Okay, so this is my output. Okay, yeah, wait a second. So for logistic regression, it shows my confusion metric here, and then the accuracy score here, and all what is my mean accuracy, and the standard deviation, precision recall, and F1 score is also given. Similarly, for SPM also, again, it's giving me all these values. Okay, what is my confusion matrix, and then how my precision recall, F1, those things are calculated, and the k-fold validation mean accuracy as well. K nearest neighbors also, I'm getting the same values. Okay. So similarly, now I have multiple models that I can select from. Okay. So then I have K nearest neighbors with 79% accuracy. Here in decision trees, I have 93% accuracy or 87% overall accuracy. And here random forest, I have 90% accuracy with k-fold 96% accuracy, right? From these, if you were to select a model out of all these to use for your future predictions, which one would you go with? Which one would you go with? Can someone tell me? So I would look for highest accuracy. So I would either choose a random forest or XG boost. Okay, random forest or XG boost. No, even decision tree I might consider. So now I have narrowed my options down to decision tree, random forest, and XG boost. Okay. Then what we can do is we can do some hyperparameter tuning as well for this. Okay, so this is how my I have just sorted all these values that I have taken into here, right, to see what is my accuracies and all. And you see that the accuracy is highest for XG boost, random forest, and the decision trees, right? So I mean, for the further developments, now I have narrowed down my options. So I started with many models, right? Many models I started with, and now I'm choosing only few out of these by looking at the accuracy. And I select, okay, I can go ahead with either XG boost or random forest or even decision tree, right? Then what we can do is we can then tune in the models. So tuning the models, you can either use a grid search or random search or even Bayesian search. So I'm going to use grid search. So grid search CV is a library function that is member of sklearn model selection package, and it helps loop through predefined hyperparameters and fit your estimator or model on your training set. So in this N, you can select best parameters from the listed hyperparameters. So what I'm going to do is I'm going to create some grid models. Okay. So for logistic regression, I have specified this C as 0.725, 0.5, 0.751, and also random state also given as 0. And then for k nearest neighbors also, number of neighbors I have given as 5, 7, 8, and 10. And the metric is also given as this. So SCV also, I'm going to specify C, the coefficients, and for the decision tree classifier also, I'm going to give some criterion. And random forest classifier also, again, some estimators, and for XG classifier, some learning rate likewise. So what you can do is you can, when you're choosing XG boost or something, you can go for the documentation provided in sklearn and see what are the hyperparameters you can tune, and then you can do some research and decide on some values. Okay. Then what I'm going to do is I'm going to for all these grid models I have, I'm going to do a grid search. So grid search, if you remember, it is going to check for all possible combinations I have. Okay. From grid search, I will again get some accuracies and some best parameters. So what it says is for logistic regression. So if you checked, I provided different types of Cs, right? 0.25, 0.5, 0.751 likewise. And it says I can, the best parameters that I can use is C as 0.25. And similarly, for k nearest neighbors also, it says you can use matrix as Euclidean and number of neighbors as 5. For SCB, C as 0.25, kernel as linear, random state, likewise. Even for decision trees, the criterion to be Guinness score, random forest also Guinness score, likewise. Okay. And yeah, so this is to see what are the hyperparameter tuning and what are the hyperparameter values we can choose for our models. Then once we obtain all these best parameters and for our models, then we can go ahead and create a final model, right? So looking at the output of the grid search, we can determine the random forest and the XGBoost seems the best fit model, right? So we already saw that random forest and XGBoost, they had good accuracy. And now from here also we see that decision tree, the random forest classifier and the XGBoost has a very good accuracy, right? 96.2 and here 94.54. So we are going to go ahead with that one with the suggested hyperparameters like evaluation metric error, learning rate 0.1 for this one. And for random forest, the criterion Guinea and the N estimate is 100 and the random state 0. Okay. So then we have to again fit the random forest model and the XGBoost model with these given hyperparameters. Okay. So now for when I'm specifying or instantiating my random forest classifier, now I'm going to give these hyperparameters as well. I say the criterion to be Guinea, number of estimators to be 100 now, and random state to be 0. And then I'm going to fit this model again and take the confusion matrix and see how the accuracy scores are. And then I'm going to visualize it and see. Okay. So this is how the values are going to look like and the accuracy score is going to look like. This is my confusion matrix. And similarly, I can do it for my XGBoost classifier as well. I can specify the find out the hyperparameters we tuned, the found out values, and then I can fit the values again and get some outputs and get the final model. So the after hyperparameter tuning only, now we have decided our final models, right? So the final models that we chose was this either XGBoost classifier with these hyperparameters or else my random forest classifier with these hyperparameter values. Okay. So with these two also we can check what is the accuracy. And it seems like this has a higher accuracy. So I'm going to go ahead with random forest classifier for my stroke prediction. Yeah. So that is the conclusion I have. Yeah, so that's pretty much it. When we do the model building and evaluation, that's how we usually work on that one. So if I'm going to summarize what I did, uh, before we actually start working on the model, we have to do all this data pre-processing as well as feature engineering, feature selection part. Once we are done that, we can split our data set into two, training data set and the testing data set, right? But if we are having some imbalanced data set or anything, we have to do some remedies for that, like oversampling that we did here, so that I can have a balanced data set. Now here also we applied that oversampling here, and we got the data set with similar values for both people with stroke as well as not stroke, right? Then what I did was I just randomly thought that I can work on this random forests and all, like some list of models that I can use on, and I fit the model, right? Then I checked the accuracy and I decided, okay, by looking at these models, I feel like I can go ahead with few of these models, and from there I selected two, XGBoost and the random forest. Also, then for those ones, I did search to do some hyperparameter tuning. So for the same model, so I selected the model random forest, and for that also I can have multiple variations by adjusting different hyperparameters. So what I did was I just specified some hyperparameter values and I checked the accuracies, how good they are. I checked it for the um, models as well for just for to see how it works. But I already knew that my best performing models were already random forest and gradient boosting model, right? So for those also I then did some hyperparameter tuning, and then from hyperparameter tuning I understood that okay, with these are the best parameter numbers I can go with, and then I got those numbers and I'm going to fit the same model again with those evaluation metrics and learning rates and all these hyperparameters, and I created another model using this one, and then I fitted the model again and saw the accuracy, and I decided by looking at those two instances again the best values were given using what do you call the random forest. So I'm going to stick with a random forest classifier with these criterions for my data set. So that is how I came into the conclusion. Okay. Yeah, so that's about it for the demo as well. Are there any more questions? If the model performance is very different on each split, what is the next step we are doing cross validation? No, in cross validation, we are getting an average value, right? For the when we are cross validating, we take an average value for all these validations. So even though it is like very different in each split, we are going to consider the average value that we are getting for cross validated ones. Uh, can we get the collab sheet for reference and practice? I can send it to you, but I'm not really sure how it would work. I have to check with the organizers, but I mean, from my end, I have no objection on sending it. Yeah. Any other questions? Also, these codes, once you understand the concept, you don't have to remember the code snippets. Huh? What you can do is, you can always search it up and say how, well, if you know what is the step that you have to do, you can search the code up and get it. Like someone else might have already done that code. Okay. Yeah. Anything else? Have I answered all the questions? Yeah. I think I have answered all the questions. Rashmi, I think we are good, right?
Yeah. So, as we wrap up today's workshop, I'd like to express our gratitude to Miss Anurangi from Octave for her valuable insight and all of you active participation. Before we end the meeting, I would like to request everyone to switch on your cameras to take a picture for today's session. Okay, thank you everyone. We hope you leave today's session with a deeper understanding of model building and evaluation. Don't forget that we have more exciting sessions lined up, so mark your calendar and stay tuned for updates on upcoming events. Thank you everyone for joining today's meeting.
Thank you.